Hi everyone, welcome to this week's tutorial. To start off with, I'm going to go through this additional example. What we're trying to do here is if I have a force from the liquid and from the gas, I'm trying to work out how much force I need to place here, or to be held by a bolt, in order to keep the gate shut. So, three things we're looking for: force of the liquid, force of the gas, force of the bolt. So, let's start with the liquid. So our x bar, remember our x bar is to the midpoint or the center of the plate, which is obviously 1000 plus half of 500. So x bar is equal to 1.25 meters. Alright, the force due to the liquid component, so F liquid, that is equal to just our formula, rho G A x bar, which equals to 850 times 9.81 times the area of our gate. Alright, circular gate of 500 millimeters, so that is pi by d squared all over 4 times 1.25 meters. This here gives us 2.05 kilonewtons. This is the force due to the liquid. So this one here. Now what I want to do is I want to work out the F of the gas. So my force gas is equal to pressure times the area it's acting on. Remember that liquid, as we get deeper, what happens is the force component increases, so it's uniformly increasing. For the gas, so it's linearly increasing. For the gas it is uniform, the pressure is in all directions. So what we get is we get a constant force profile like this. So no matter where it is, alright, this 10 kPa is felt here, 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 the whole way through. So force of the gas is equal to 10 times by the area of this one here, which is pi by 0.5 squared all over 4. Which gives us the answer of 1.96 kilonewtons. Alright, so that's our force in the liquid, the force in the gas. Now, what I need to do is work out the force in the bolt. Now, to do that, I need to calculate a few things. Got force in the liquid, force in the gas. The force in the gas, sorry, I'll redraw these again. The force in the gas is like this. What it means is the actual force is felt halfway. This one here is obviously a third from the base, which we use our formula for, our Y bar formula. But what that means is the gas, the force of that is felt at X bar. Alright, so the gas force sits at X bar is 1.25 meters. However, for the liquid, what we need to do is we need to calculate the Y bar. So Y bar, for where the liquid force is acting, is equal to X bar plus K squared on X bar. Being circular, alright, we get a different formula here, but what we're going to end up with is we're going to end up with 1.25 plus, so go back through your notes and you can work out the K. What we end up with is 1.25 plus 0.5 squared, so D all over 16 times by 1.25. And this here, just going to punch into the calculator. 0.5 squared divided by 16 times 1.25 plus 1.25. Cool. We end up with 1.2625 meters. That is Y bar here. Alright, so K is equal to D on 4 for a circle. So now what I need to work out is I need to calculate the force in the bolt. So what I'll do first is I'll just draw in a diagram. So I have the tank, the gate, something like this, where this point here is a meter, 500. Now what I know is my X bar is 1.25 meters. I know my X bar is equal to 1.2625 meters. Alright. And I have my bolt sitting down here, FB. So along this line here, this is my F of my liquid, and along the center line here is the F of the gas. So what I'm going to do is I'm going to take this section here and make it a bit bigger. So all we're going to look at is the gate. It's a free body diagram of the gate. So here, 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 FB, F liquid, F gas. Let's draw with blue. So this here is sitting at 500. This here is obviously sitting at 0.25, it's at halfway. This one here is sitting at 0.2625. So all I need to do is force by lever arm. That should be 0.5, sorry. Let me clear that up. Just converting all to meters. So what I end up with, therefore, 0.5 FB equals to 0.25 FG plus 0.2625 force of the liquid. Now what we can do is we know this, so it's equal to times, that was 1.96 kilonewtons plus 0.2625 times this here was our 2.05 kilonewtons. Rearrange, so work this out. Alright, divide it. What you'll end up with is the force in that bolt is equal to 2.06 kilonewtons. Alright, that is how we solve this first one here. So what we've worked out is the force here required to balance the force of the liquid and the force of the gas, 2.06 kilonewtons. Cool. Now, the next thing we need to look at is I'm going to do 1 and 2. I'm going to leave question 3 for class when we go when we meet up on Tuesday. So let's start with question 1. So where are we? Q1. What do I have here? Well, what I have to start off with is I have a dam wall is 6 meters wide, 10 meters deep, and the water is at the top level here. And I am calculating. What am I calculating? Calculate the force on the wall and the distance from the top where the force may be considered to act. Alright, so how am I going to go about this? Well, I want to work out force. I want to work out Y bar. Y bar, remember this here, is to the center of pressure, CP. So let's go through and let's work out force first. So to calculate force, there's a few ways to do it, but I'm going to use the pressure method. So P is equal to rho G H, so it's water, just going to double check that on my calculator. Yep, I have made a mistake already because I was too trusting. Why have I done that? Y10, that should be 5. Okay, being a square, it should act where you're going to take it to the centroid. So this here, sorry, this pressure is the pressure at the centroid. So therefore the force on the wall is equal to PA, which equals to 49 times 6 meters times 10 meters. What this is going to give you, 49 by 6 by 10, 2.94 mega newtons of force. Alright, so remember we get the average pressure at the centroid, we can calculate the force. Alright, go through your notes and this will be seen in there. So now we've calculated the force, I need to calculate where this is sitting, so I'm calculating my Y bar. So I know X bar equals 5, so Y bar equals X bar plus K squared on X bar, which equals to 5 plus K squared. So K squared, K for a rectangle is the depth divided by square root 12. K squared equals D squared on 12. So 10 squared all over 12 times by 5. What you'll end up here is 6.67 meters. Alright, so that is where it is acting. So the force is acting here, 6.67. Now we just summarise, so therefore force of 2.94 meganewtons acts at 7 meters below top of, whoa, that is our summary. Check. Alright, question 1 done. Now, question 2. Let's just erase this again. Cool. Question 2. Circular door, 0.8 meters in diameter, is located on a wall of a tank. We've got the axis of the door 1.4 meters below the waterline. Blah blah blah. It's pivoted about the horizontal center line. Calculate the torque. Alright, so let's do that. So I have a tank. And in here I have a gate. Now the center line of that gate is 1.4 meters below. And I have a hinge sitting here. So I've also got the diameter 0.8 meters. Waterline. Cool. So again, I'll use the pressure method. P is equal to rho G H. It's water. It's my rho of 1,000. Gravity. My height is 1.4 meters, which gives me alright 13.7 kPa. Awesome. Now the force is equal to the pressure times area times pi by 0.8 squared 4 equals 6.89 kilonewtons. So this is the force acting here. Now I'm going to work out where it's acting. My x bar is 1.4. Y bar is x bar plus k squared on x bar, which equals 1.4 plus, so for a circle, k is d on 4, square this, so therefore k squared, d squared on 16. So what do I end up with here? I end up with 0.8 squared, 16 times 1.4 equals, where are we? 1.4286 meters from the top. So I'm 28.6 millimeters further down. Alright. So that's where the force is acting. So what I'm trying to work out now is if I have a force acting along here, well, how much force do I need to put on the other side here to balance it out? Alright, or how much torque do I need? So the way torque works, so torque is, I think it's tau, is the same as calculating a moment. It's the force times by the lever arm. So if I have a force sitting here, point here, this is the force. Force, the distance is the lever arm, which is equal to force 6.89 kilonewtons times the lever arm. Well, the lever arm is just y bar take x bar in this case, so it's going to be 28 millimeters, so converting that to meters, 28.6, so what I end up with is 197. Now torque is measured in Newton meters or kilonewton meters, exactly the same as our moments. Alright, so there's what we need to do, let's calculate that. And so our summary, therefore, to keep our gate closed, we need to apply a torque of 197 Newton meters. Awesome, that is our summary. Question 2 done. Let's go here. Now, question 3. What you're going to need to do, just a heads up, is you're going to need to calculate. I would use the pressure method to calculate the pressure, then calculate the force, calculate where it's sitting. Another important thing to note is in this drawing, or in this question, what you have is you have a tank sitting like this. At some point here you've got its centroid. You know this distance here. Now the centroid of a shape is completely at this x-axis, which means this is also a centroid. Alright, that's going to help you. You need to calculate pressure here. You also need to calculate pressure here, but you'll be using measurements this direction. So just be aware, but I think this is a key piece of information that you're going to need. So we will cross that on Tuesday when I see you. Good luck, have fun, and I hope this helped.